All right, hello everybody. In this screencast, I'm going to, as promised, walk through possible solutions for homework 2.67, 2.73, and 2.85, which we were working through in class the other day. So let's go ahead and jump right in. 2.67 gives us this problem where we've been given a function called bad int size is 32, and basically we need to make this into a good int size is 32. And the problem that we have is that this particular function, for instance, if compiled on certain machines, will give us a warning or an error. The book tells us that if this is compiled on a 32-bit SunSpark, it will tell us, warning, left shift count is greater than or equal to width of type. Okay, why do we care? Well, and actually I think they go on to say that when you execute it on that particular machine, you get the wrong, it gives you a 0 when it shouldn't, okay? So, in a nutshell, the problem that we have here is that the behavior on a 32-bit machine when we do a 32-bit shift to the left is undefined. And that's not without cause. There are different ways of interpreting intent when someone is trying to shift at or beyond the word length on a particular machine. So because of this, it actually does make sense to say, well, we don't know exactly what you're after, so we're going to say that's undefined. It turns out on a Spark machine, as they explain, let's see here, I think they explain. Let's see. Oh, they don't mention it here, so I will mention it. On the Spark machine, it turns out that if we try to shift 32 bits or more, those are ignored. Basically a mod operator, mod 32, is applied to the shift amount. Okay, so we end up with a 0 if we try to shift 32 bits. If we try to shift 33 bits, we'll get a 1. And this is because basically all of the upper bits beyond the lower 5 end up being ignored. Okay, so how do we fix this? Okay. So the question is actually broken into 3 parts. Let's see, did I? No, I did not. The first part, part A, simply asks us to explain what way does the code fail to comply with the C standard. And again, the C standard does not actually define the effect of shifting by the word length. So for instance, shifting by 32 bits on a 32-bit machine, that's undefined. Okay, so we shouldn't do that. That's why we're out of compliance with the C standard in that case. So simple answer there. So what can we do? We need to then modify the code to run properly on any machine for which the data type int is at least 32 bits. So how could we do that? Well, one way we could do that, let's see if my pen will work here, would be to change the way we shift. So on a 32-bit machine, notice that this line of code would be okay. We can shift 31 bits and we don't have a problem. In the case of this line of code here, we have a problem. Now, there are a couple ways that could be dealt with. We could break up the shift, so instead of shifting 32 bits, maybe we say we shift 31 bits and then take that result and shift it another bit. Okay. So that's one thing we could do. Another interesting solution would be, instead of putting a 1 in there and shifting it 32 bits, well, what if we put a 2 and shifted it 31 bits? And if you think about it, you'll notice that that would have the exact same effect. That should be putting that bit just past the most significant bit of a 32-bit word, at which point the rest of the function would work the way that it was intended to. Okay. Part B then, part C asks us to modify the code to run properly on any machine for which data type int is at least 16 bits. Okay, so on a 16-bit machine, then obviously this is a no-no, but actually so is this. So how are we going to get around that? Okay, well, again, we can use multiple shifts in order to accomplish our goal. So let's look first at set MSB, where we want to shift 31 bits. So why don't we say set, and again, this On a 16-bit machine, obviously we're going to get bits false. It's not a 16-bit, or excuse me, it's not a 32-bit machine, but we want this to compile properly. Okay, so we need this code to be legitimate on a 16-bit machine. So how can we do that? Well, we could just set the most significant bit instead as 2 left shifted 15 bits, and then left shifted 15 bits again. And again, we're playing the game that I mentioned before, where instead of sticking a 1 and shifting it 31 bits, we're now using a 2 and shifting it a total of 30 bits. Okay? And the key here is that this behavior is not undefined. And once we have that value, this behavior, okay, this shift here, is not undefined. We know exactly what happens there. So it's not that the machine doesn't want us to push bits off to the left. It just doesn't want us to do them all at once. It's really what it amounts to. Okay, so doing this, then we could set the most significant bit. Notice then that again with this line of code right here, we're really just trying to get that bit one position further than we put it here. So kind of a clever way that we could use some of the work we already did is simply to set it to set MSB shifted by 1 bit. And that obviously isn't going to give us any trouble. Okay, so that is one way you might have tackled 2.67. Let's jump on to the next one. If I can get out of annotation mode here. Discard those changes. Okay. Maybe. There we go. Okay. 2.73. Addition that saturates to tmin or tmax. So we're supposed to create this function with the prototype of int saturating underscore add int x int y, and we have to follow the bit level integer coding rules on page 128. So how are we going to do this? Whoops, that's not what I want. I want to jump over here. So what I've got here is I've actually just coded up a simple kind of test program that I want to be able to use to test my solution. And this is something that I highly suggest you do. Don't just think of a solution. Think of a solution and think of how you might check to see that it works. One way is to code it up and see if you get the behavior that you expect. Okay? So just a quick walkthrough here. You see the prototype on the top, and then in my main function, I'm creating 2 int variables a and b, giving them both rather large integer values, and then I have a series of, let's see, 1, 2, 3, 4, 5, 6 printf statements, wherein all I'm doing is showing the comparison first of adding 2 values a and b, just using the addition operator, and then comparing that to the results that I get by calling this function saturating add, so I could compare the results. Okay, and then after that, you see me flipping the sign, negative a and negative b, and then finally flipping one of the signs so that we have operands of different signs, negative a and positive b. You get the idea. Okay, so let's just quickly verify that this even works. Okay, so you'll see here that I'm compiling using the GCC compiler, and I'm setting the 32-bit flag, -M32, so I'm going to get a 32-bit binary. I'm doing this to enforce the size of an int. And I've just called this source file 2.73.c. Okay, so it compiles without a problem. I did not specify the name of the executable, so it is simply a.out. And when I run this, what do we see? Okay. Now, if you look back at my source code, you'll notice that right now saturating underscore add is simply returning the sum of x plus y. So it is doing the exact same thing down there that I'm doing in line in these printf statements up above. Okay, so this is what we'd expect. We'd expect to see the exact same results coming back from our saturating add function. Okay, so no surprises here. So we have a working piece of code. Now let's make it do what we want. So again, we're supposed to make sure that this function returns, let's see here. We want to return Tmax when there is positive overflow, Tmin when there is negative overflow, and in all other cases we just want to return the value that we actually got. Okay, so to do this, I want to just kind of brainstorm for a minute in terms of, well, how might we go about this? Okay, and you'll recall we had a discussion in one of the screencasts earlier about how in a CPU we don't actually say within the ALU, one way to build an ALU is to, instead of have something fancy that decides if we're going to add or if we're going to multiply and so on and so forth, one way to do it is to say, well, I'm always going to add. Okay, so I have something that adds, and I'm always going to multiply, and so forth. And then what I'll do is I'll select between those results, so that if I wanted to multiply, so this is A and B going in here, and this is also A and B going in here. So if I wanted to multiply, then I would, for instance, put a 1 on this line, and I would get the results of the multiplication. And if I wanted to add, I would put a 0 on this line, and I'd get the results of the addition. Okay, so in other words, compute all the things that you want, and then select the one that you need. All right, so that's a strategy that I'm going to show you how we could use in this case. All right, so let's jump back over here. So basically, I propose that there are 3 different things that could happen. One is that we could have different signs. And note that if we have different signs for x and y, then overflow isn't possible. Okay? We could also have the situation where we have 2 negative values. In that situation, the operands would be negative, and the result should also be negative. If it's not, and it's positive, that means we've had an overflow, so we'll need to deal with that. And we could have the situation where we have 2 positive values. Okay? And in the end, we want to choose between these things. So instead of returning x, y, what I propose we do is that we say, okay, I'm going to have a result. Let's see here. I have 3 possible results. I could have a result that I get when I've had different signs. I could have a result that I get when I have negative value, 2 negative signs, if you will, 2 negative values. Okay, and I could get a result, let's pop up one here. Third result, when I have 2 positive values. All right, and then I would need to select between those. Well, how do we do that with the limited operations that we've been given? One way of doing this would be to make sure that only the condition we're looking for has bits that are 1, and then in every other situation, all the bits are 0. In other words, I would like for, if we have different signs, to get a result in result 1 that is valid, and always have all 0s in result 2 and result 3. Okay, likewise, if I have 2 negative values, then I would like for result 2 to have a useful value in it, and for result 3 and result 1 to have all 0s. Okay, and the same thing applying to result 3. Why? Well, because then I can do this. If I return result 1, bitwise, lots of spaces, bitwise ORed with result 2, bitwise ORed with result 3. Okay, so think about how this would work. If the result is supposed to be 0, they're all going to be 0, and we would simply return a 0. If the result comes from having different signs, and we can make it so that we have a valid answer here, and that these are all 0s, then the bits in result 1 that are 1s would carry through this OR operation, and these are all 0s, so they won't have any effect. Okay, so think about that. Try to get it to make sense in your mind. And let's just go ahead and actually make sure that we haven't done anything fishy here. It's a good idea to, it's a good idea to compile, test your code regularly. So you know, notice I've already got an error. I missed a semicolon right here. Okay, so it's good to catch little mistakes like that early so that we're not hunting for them as our code gets larger. Okay, so now you see the behavior's changed in that now we always get zeros from our saturated add, and that makes sense because every one of those results is set to 0. Okay, let's go ahead and jump in then and tackle these problems one at a time. First, let's look at the situation in which overflow is not possible. Okay, so that's right here where we have different signs. How am I going to know if I have different signs? Well, I need to be able to look at the sign bits first of all. So let's give that a try. How can I isolate the sign bit? Well, the most significant bit, and I'm going to create a mask that's going to look just at the most significant bit, can be identified or masked, how do I say that, isolated, by using this macro we're allowed to use, which is int min. So no matter what the size of our machine is, if we're allowed to use int min, which I have access to through this limits.h file, okay, this is the minimum signed value. Okay, so if you think about that, that's going to be a 1 in the most significant bit and zeros the rest of the way. Okay, on whatever machine I'm on, if it's 4 bits, I'll have a 1 and 3 zeros. If it's 8 bits, I'll have a 1 followed by 7 zeros, and so forth. So this is nice portable code that we're writing here. Good practice if we can do it. So by including, again, this limits.h file, I can do this. So MSB mask now contains a 1 in the most significant bit and zeros everywhere else. Okay, so let's just remind ourselves of that. This is 1 followed by some zeros, and then it ends in zeros. Okay? All right, next step. So we have the ability then to isolate the most significant bit, or that sign bit. What are we going to do with it? Well, we want to know if it's possible for there to be an overflow. If there's going to be an overflow, then that means that, pardon me, okay, so that means that there's a difference between those bits. Okay, so I'm going to go ahead and check for that. So we'll call this variable not possible overflow mask. All right, so what I want this to be is a mask that is all 1s if it's not possible for there to be an overflow, and is all 0s if it is possible for there to be an overflow. In other words, I want it to be all 1s if the signs are different. The way I'm going to use that mask is that in setting the result, I'm going to say not possible overflow mask. I'm going to end that with what the normal result could be. So if it's not possible for there to have been an overflow, then I just want the sum, and I want to return it. Okay, so if I've computed the sum, and I can create this cool mask that's going to be all 1s if I know there wasn't an overflow, and all 0s if there possibly was an overflow, then this line here will make sure that whenever the signs were different and it's not possible that there's an overflow, then result 1 will have a meaningful value in it, and otherwise it'll just have 0 in it. Okay, so we need to figure out this mask. So when would it not be possible if there would be an overflow? Well, that's in the situation in which the sign bits for x and y are different. How can we figure that out? Well, if I and x with the most significant bit mask, that isolates the sign bit for the x argument. Now, if I XOR that with the y value that I've ANDed with the most significant bit mask, then I'm doing an XOR operation on the most significant bit, and all the others are 0s, so I know they're going to be 0s. What does that mean? Well, that means if there's a 1 in the x but not in the y, we'll get a 1. If there's a 1 in the y but not in the x, we'll get a 1. If there's a 1 in both, we'll get a 0, and if there's a 0 in both, we'll get a 0. Okay, so only in a situation where the signs of x and y are different will this expression give me a 1. it will give me a 1 in the most significant bit. Now, if I right shift 31 bits, think about what just happened. I'm going to sign extend. So if that expression gave me a 1, then I will now have 1s all the way across. I'll have 32 1s. If it gave me a 0, I'll have 32 zeros. So I have exactly what I wanted. If those two signs are different, then I'll have a mask filled with 1s, and if they're the same, I'll have a mask filled with zeros, and so my result will only show up as a non-zero value if indeed the signs are different. So let's test this. What we'd expect is that down here, where we have different signs, we'll expect that we won't see a 0 anymore. We'll expect that we'll see 9993000, right? We'll expect to see the correct answer. So let's compile this and let it run. And voila. Okay, so that worked great. So we solved a third of the problem. All right, now let's look at the issue of having two negative values. We're going to use a similar scheme. So we only want result 2 to not be 0 in a situation in which we have two negative values. Okay, so I'm going to use a mask called two negatives mask. Oops, I can't spell. Two negatives mask. And I'm going to AND that with some stuff. Okay, so we'll come back to that. So it's the same scheme. Not possible overflow mask. That's only going to be all 1s when the signs are different. Now we're going to have this two negatives mask, and I want this to be all 1s when the signs are the same and they are negative. Okay? So first, let's isolate the sign bit from the sum. Okay? So I'm going to create a variable called sum sign, and we'll set this to sum ANDed with the most significant bit mask. All right, so sum sign now is just, it's going to have 0 in all positions except possibly for the sign bit, because we've ANDed that with something that was all zeros except for a 1 in the sign bit. Okay, now we need to set this mask up. Two negatives mask. Okay, so how can we tell if we had two negatives? Well, we can do something similar to what we did before, right? So before we looked at, see if I can just copy this. We looked at the two bits, in the two most significant bits in X and Y, and we XOR'd them because we wanted them to be different. Now we want them to be the same, and we want them to be 1s. So if we just AND this instead of XORing, then we'll only get a 1 from that expression if they're both the same and they're both 1. All right, so that's a piece of cake. Okay. However, you'll notice that's only half the battle. So we know that both of the signs are negative, so that means that we want to look at this result too, but we also need to know, do I take the result of the summation because there wasn't overflow, or do I want to set the value of the summation to t-min, okay, because there was a negative overflow? All right, so we need to make that determination. So we've already assumed for this block of code, we're going to assume we do have two negatives. If we don't have two negatives, then this mask is going to zero out our answer for result 2 anyway, so it won't matter. So we can just pretend that we have two negatives, okay? Think of this in isolation. So if I have two negatives, how do I know if I want to keep the value? Well, I know based on the sum of the sign, because if the sum of the sign is negative, then I added two negatives and I got a negative, so I didn't have overflow, right? So if I take the sum of the sign and I just right shift that by 31 bits, this is an arithmetic shift, so if it's negative I'll get 1s all the way across, if it's positive I'll get 0s all the way across. So if I want to keep the value of the sum, then, excuse me, if it's negative, then I want to keep it, and the way I'll do that is I'll use this keep value mask and set it to all 1s in that condition. Okay, how does that solve our problem? Okay, so you may want to look at this multiple times. Let's see here. Oops, I'm getting ahead of myself a little bit. This is going to look a little tricky. But if you think about it, it will eventually make sense. Okay, so two negatives masked. So this is going to give us all zeros unless both values that are being added are negative. Okay, and we're accomplishing that with this AND. Now we need to AND that with either the value we got when we added the two numbers, or if there was overflow, we need to AND it with the value that the largest negative value that we can have, right? So in other words, tmin. So how can we do this? Well, let's think for a minute. If I've got this keep value masked. Okay, so if I want to keep the sum, that would be the situation in which the keep value mask is all ones. Okay, so if I AND, bitwise AND, the keep value mask with sum, I'll get all zeros if I don't want to keep it, and I'll get whatever the sum was if I do want to keep it. Okay, why do I care about that? Well, I'm using a similar strategy in this small section of code that we're using in the larger code, right, where we're saying, okay, maybe we'll compute two different things, then we'll decide which one we want. So on this side, what I've got right here is what I would want if I actually wanted to keep the sum. Or it's possible that I don't want the sum, but that what I want is int min. Okay? How do I know if I want int min? Well, I want int min when I don't keep the value because there was overflow. Okay, so again, if the keep value mask is all ones, that means there was not overflow. If it's all ones, then when I do this bitwise negation of that variable, I get all zeros. All zeros ANDed with int min will give me all zeros. All zeros ORed with this thing over here is going to give me whatever this thing over here is. Conversely, if and let's go on. If the keep value mask, have a typo there, was all ones, then this AND would end up, this bitwise AND would give us the sum. So we have then the sum being ORed with, if keep value mask was all ones, with a zero on this side, a bunch of zeros. So we would have this result. Okay? That would be being ANDed with two negatives mask, which should be all ones in the situation we're talking about, which would go into our result. All right, so what we've done is basically created kind of an if. If I have two negatives, then my two negatives mask will be all ones. So if I have two negatives and, okay, something over here, okay, what's happening over here? Well, if my sum has not overflown, which I've determined with this mask, then I'll take it because it will be ANDed with the keep value mask. Or I will take int min. So if there's no overflow, then I'm going to return the sum. Otherwise, I will return int min. Okay? That looks tricky. There's a lot going on there. There are a lot of bits involved and several operators. So please look at that and think about it and kind of walk through it a few times. Put in some bits if you need to. Let's go ahead here and compile it. See if she works. All right, so at this point, I am looking at the situation where I have two negatives. That's happening right here. And you'll notice that there is overflow, and that's why the normal addition goes positive. But our nifty little routine here now actually saturates the value at the tmin that we're looking for. Okay, so we're 2/3 of the way there. Let's finish this up with two positive values. Pardon me. We'll use the same scheme again. So we're going to have a mask called two positives mask. And we're going to bitwise AND that with some stuff. Well, what stuff are we after? Well, we're either going to be after the sum or we're going to be after int max, okay, or tmax as the book calls it. So first, let's determine if we want to keep the value or not. Well, no, let's back up. Let's determine first if we have two positives. Two positives mask. How can we do that? Well, again, this is going to be kind of similar to what we did up here. I can get this down here with the negatives, except in this case, we want to make sure that the sign bit is not set. So how could we do that? Well, one way we could do it is instead of ANDing it with this most significant bit mask, we could XOR it, because there's a 1 in the most significant bit mask. So if there's a 0 in the most significant bit, XORed with a 1 here in the most significant bit, we'll get a 1. Okay, indicating what we want, that there was a positive value there. And we're going to then AND that with the same thing done over here with the Y. Okay, so if X and Y both have a 0 in their most significant bit, then this XOR operation here and this one here will both return a 1 in the most significant bit. They'll be ANDed together, return a 1, and we will right shift it 31 bits, smearing that 1 all the way across, so we'll have a bunch of 1s. So in the case that both X and Y are positive, our two positives mask will be all 1s. All right, so there's half the battle for this particular piece. Now we need to decide what we're going to take. If we want to keep the value, let me type this real quick here. We need to decide whether we want to keep the value we got when we added these two numbers that had positive signs, or if we want to, if we've seen overflow and we actually just want to keep, we want to send the int max. Okay, so how can we do this? I'm just going to use the same variable, keep value mask. We're done with it for the negatives. We can use it for the positives. So we want it to be all 1s if we didn't have overflow. Well, how do we know we didn't have overflow? We know we didn't have overflow if when we added these two positive numbers, we still have a positive number. Okay, so how are we going to know that? Well, we already, earlier we calculated, earlier we calculated the most significant bit, or rather the sign bit, of the sum. We called it sum sign. So we know what the sign is. Now what we need to know is what we want to do is that if it's a 1, that's a problem. Okay, if it's a 0, then we're fine. So what can we do? Well, we can use the same trick we did on the line before. We'll just XOR it with most significant bit mask. Okay, so now if the sum sign is 0 and we XOR that with the MSB mask, which has a 1 in the most significant bit, then we'll have a 1. And so then if we right shift that 31 bits, we'll have a bunch of 1s. If the sum sign is a 1, we've XORed it with MSB mask, we'll have a 0. Okay, because they would both be 1s then, so we'll have a 0. And so we'd have a bunch of 0s in our keep value mask. Okay? So all that's left now is to finish populating our result. And this is going to look familiar. So we did our two positive mask. We're going to AND that then with some result. And we need to pick between two things again, so we're going to use this bitwise OR operator. And we'll use a similar scheme as we did above. We're going to use one expression to compute, or to get a bunch of zeros if, to get the sum if we want it, and to get a bunch of zeros if we don't. And on the other side, we'll have the bits for int max if that's what we want, and we'll have a bunch of zeros if we don't. Okay, so we'll, in this case, we're going to AND the sum again with keep value mask. Okay, because again, if we want to keep the value, that will have all 1s in it. So we'll just AND that with a sum. If we don't want to keep the value, then the keep value mask will have zeros in it, and that'll be a 0 over there. And then we do basically the opposite with int max on this side. So int max is a macro that will have the largest possible positive value in it that we can represent. We'll AND that then with a bitwise negation of the keep value mask. So we get the opposite behavior on that side. Okay, so let's go ahead and compile that. And look at that. So now we have all three pieces working. Here we had positive overflow where we added two large positive values and got a negative one with normal addition. And here's the value we now get with our saturated addition function. Okay, now we don't want to just trust those one values, right? So we'll actually go with smaller values that shouldn't cause overflow in either direction now. And let's make sure that we should get the same answers in each case. So here we see large positive values, large negative values, and the same big positive value, though not as large. All right? So there you go. There is one way to solve that problem. Maybe it's not quite as pretty as what you would have written in C, but notice that now we've built this complex behavior using just these simple operators. So I think that's pretty cool. All right, let's jump away from this now and look at the last one that we had, 2.85. This problem was asking us to, what's the wording they used? Give a floating point format, given the floating point format with a k-bit exponent and n-bit fraction, write formulas for the exponent e, the significand m, the fraction f, and the value v for the quantities that follow. In addition, describe the bit representation. Let's hit these one at a time. By formulas, they're simply meaning, show us the bits, obviously in the case of number 7, explain what they would be, and then on the other two, describe, in general terms what the others would have to be, what E and M and F and so forth. Okay, look, it's just probably easier just to jump in and do it than to try to explain it. All right, so with the first one, we've got the number 7. Okay, and we don't know anything about this particular machine. We don't know its word size, but there's some things we do know. We know it's using a floating point, your typical floating point representation. So we have a sign bit, okay, and that's 1 bit, and we have an exponent portion, okay, and we'll call that k bits, and then we have, we'll call it the mantissa. Well, they don't like that. Let's see here, what do they want to call that? They're calling this F, or the significand. That's what I'll put, the significand. Okay, and that's going to be n bits. So let's look at this. First, the number 7. Well, 7 is equal to 1, 1, 1, right? We have 2 to the 0 plus 2 to the 1 plus 2 to the 2. 4, doing this right, yes, 4, 2, and 1 equals 7. Okay, so we know that's what the bits would be, the integer value. How do we make this a floating point value? Well, remember that we first move that decimal, or excuse me, that binary point, so that we have 1.11 times 2 to the 2nd power. Okay, so our exponent, let's see, I've called this the exponent here. Yeah, okay, so I'm going to say E. Don't like this, but we'll use this capital E. This is going to be equal to 2. Okay, our mantissa then, I'll call it M, is going to be 1.11, which means that our significand, which the book calls F, is just going to be 1, 1. Okay, 1, 1 with a bunch of zeros behind it. All right, the final value, V, is going to be 7, because this is a number that we can represent perfectly in floating point. And the exponent bits, well, let's talk about it. What are the exponent bits going to be? So when we to determine the exponent bits, we have to use K, right? Because we know that we'll start with E in this case. I don't like that switching notation. In the book, they used a little e. So, and then in this problem, they used a big E. So I'm going to use a little e. Please note it maps back to the big E they're talking about here. But just for consistency, E, when we look at the exponent, is actually shifted by our bias. Right? We're going to subtract the bias. What is the bias? Well, our bias is equal to 2 to the k minus 1 minus 1. All right? That's our bias. So what does that look like in terms of bits? Well, 2 to the k minus 1. If I have k bits, notice that, and there are k of these, okay? That's an R, folks. All right, there are k of these. Notice that this is the 2 to the k minus 1th position, right? That position represents the power, 2 raised to the k minus 1 power. So 2 to the k minus 1, how would we represent that? Well, that's going to be 1s in the rest of these bits. Okay, no matter what k is, 2 to the k minus 1 is going to be all 1s here. Why? Well, because 2 to the k minus 1 would have been a 1 followed by a bunch of zeros, right? So if I subtract 1, then I'll simply have a 0 followed by a bunch of 1s. Okay? So this then is our bias. Now, notice that when we're sticking a number into a floating point number, we're not going to subtract the bias. That's what's going to happen when it's evaluated. When we're actually creating the floating point number from our value, we want to add the bias. So we're going to actually add this to our value. Okay? What is our value? Well, it's the exponent that we want. All right? So we're going to add 0, and then a bunch of 1s. 2, and I don't know how many, but I'm going to add those to the value 2. What's going to happen? Well, I'll get a 1 here. This can give me a 2, which rolls over to another 2. That's going to happen all the way down here till I roll over and I get a 1 there. Okay, so the exponent bits are going to look like this. So we can tell them that. We don't know how many bits there are there, but we can say this is what the exponent bits will look like. Remember, we were asked to provide, if I can find the problem here, exponent e, well, that was this too. I'm all over the page here. You'd want to clean this up in your answer, obviously. Exponent e, the significand m, well, that's this 1.11, okay? The fraction f, what is f? Well, that's this piece. We chop off the front. We don't need that 1 because it's implied. So it's just this 110. Now they talk about it as a fractional part. So please just put the binary point there just to be explicit that these bits are meant to be after the binary point. So f is 0.11. And the value v. Well, I'm not going to do the math here, but if you went back and you it should be occurring to you that because you haven't lost any bits in this process, you could reconstruct the 7 from the floating point representation for the number 7. Okay, it's one of those values in the subset that we can actually represent exactly. All right, so I'm going to go ahead and clean this off, and let's go to the next one. I've got to get out of annotation mode first. Don't need that. And let's look at B, the largest odd integer that can be represented exactly. Okay, what's the largest odd integer that can be represented exactly? Well, we know a few things about it. Recall again that we have, oops, I need to be able to write. Pardon me, what do I have going on here? Okay, here we go. The largest odd integer that can be represented exactly. So we've got, again, a sign bit, and then an exponent, and then, whoops, I want to put an int there, and then a significand. Okay. Okay, so to answer this, the largest odd integer that we can store, obviously we need to have a 1 in the units position. Okay, so when looking at our significand, we need to make sure there's a 1 way over here. And we want the largest possible thing that we can store. So these are all going to be 1s, right? How many 1s will there be? Well, there will be n 1s, right? Okay, so if I have n 1s, or rather the significand is filled with 1s, then my fractional part is just a bunch of 1s, and there are n of them. Okay, the mantissa then, as it's, well, we'll just say m rather. Okay, so This implies that there's a 1 in front of that, right, with the floating point standard we're using. So our m then will have 1.1, blah, 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 blah. And so there will actually then, we're implying that there are n plus 1 values, n plus 1 ones in this integer we're trying to represent. Now, what's the kicker here? The kicker is we don't want to shift this thing, right? We back that up. We want to shift this all the way over to here and no further. I'm getting tongue-tied today. If we shift the bit any further, then we'll have a 0 there and it'll be even. So we need to move that binary point. How many positions? Well, recall there are n ones, so we need to move it n times. Okay? So we have then in the exponent, back up here. Yes, okay, so we want our exponent to be equivalent to n. How are we going to do that? Well, remember that we need to add the bias on the way in so that when our number is evaluated, the bias can be subtracted. So our exponent needs to be n, ultimately, because we want to shift this binary point in n positions so that we'll end up with all these ones we've stored up with the dot there and have this large odd integer. Okay, so the exponent n, how do we get that? Well, we're going to need to add the bias to it. We know the bias is 2 to the k minus 1 minus 1. Okay, so that's going to be the exponent portion. What have we answered so far? So we said then the exponent needs to be n. We said that, we'll write this over here again. They're saying e. So e needs to be n. What does that mean? Well, that means that our exponent portion right here, that needs to be n plus 2 to the k minus 1 minus 1. And let's see, I already said e, what's left? F, we mentioned already, that's going to be a 0.11111. There will be n ones there. Okay, and what will the value be? Well, this is going to be, it'll be the binary representation of, well, hold on, let me back up here. Yeah, the fractional part will be a bunch of ones. Yes, so what will v be? We still needed v. That's going to be 2 to the n plus 1 minus 1. Why is it going to be that? Well, let's take a look. To understand why this is going to be our result for v, let's look again at our significand and what we're doing with the exponent. We're moving the exponent, or excuse me, not the exponent. The exponent is moving the binary point all the way over here. How many ones do I have? Well, I have the n originally. Remember, this value of m is 1 point and then all those ones. There's another 1 that's implied. So I have n plus 1 ones sitting here, right? This is the 2 to the nth position. Okay, because recall, we start at 2 to the 0. So this position right here is the 2 to the nth plus 1 position, right? And what is the difference between there being a 1 there and a bunch of zeros and there being a 0 there and a bunch of 1s? The difference is 1, right? If I added 1 to all of this, I would get all of this. Okay, so 2 to the n plus 1 minus 1 gives me this. All right, so that's v. Finally, let's look at C and see how quickly I can do this. I saw that I have a typo on my slide here. I was supposed to update that and didn't, so you'll have to forgive me. It still says the largest odd integer that can be represented exactly. What we actually want is the reciprocal of the smallest. Let's get a pen here. We want a reciprocal of the smallest positive normalized value that can have, so what will that be? Well, let's again think through this. Now we're dealing with normalized values, not denormalized. That means what? That means that in the exponent bits we're not allowed to have all zeros. And we're not allowed to have all ones. We must have something in it. Okay? Since we want the smallest positive normalized value, the reciprocal, of the smallest positive normalized value, then we want the largest negative exponent we can get. Since we subtract the bias, we want then the smallest non-zero exponent that we can have. So we're going to have a 1 with a bunch of zeros. Our sign bit will be a 0. And what are we going to have over here? Well, again, we want the smallest possible value. So we're just going to leave zeros here in the significand. And remember, there's an implied 1 at the beginning of it that we really can't get rid of. Okay? So what's this going to give us? Well, let's analyze this a little bit. This gives us the largest negative exponent that we could have. And we want to know what is the reciprocal then of, well, let me back up again. This is giving me the smallest, with that implied 1 in the front of it, it's giving me the smallest possible fractional portion I can have, and I'm multiplying it by the largest negative power of, negative exponent, okay, for a power of 2 that I can come up with, right? I need the reciprocal of that. So I've got 2 to some negative value being multiplied by a 1, right? That's what's implied by all of this. And I need the reciprocal of that. Well, that's simply going to be the, that's simply going to be negative 1 times whatever this is, right? So let's just represent this as x. So I have 2 to the x. That is not an x. I have 2 to the x times 1.00 whatever. This is not supposed to be a 1 here. Okay. All right, so there's kind of this vague thing over here we're thinking about that we know we're going to be dealing with. There's going to be some negative power and of 2 that we're multiplying by 1. We know this is as small as we can get, so this is what we need to deal with. How do we get the reciprocal? Well, again, the reciprocal is going to be just the negative of whatever x was. X is this negative question mark. Well, what is that negative question mark? What is the largest magnitude negative exponent we could have? Well, let's talk about that. That's going to be, because we're not allowed to use a biased value, this has to be, not biased. I'm tripping over my words. This has to be a normalized value. Okay, so remember, we can't have all zeros. So we had to have a 1 in the exponent. So what does that mean? Well, that means that I had to start with at least a 1. And then I could have subtracted the bias from that, right? Well, what is my bias? It's a 2 to the k minus 1 minus 1. So this is my unknown negative exponent. So to get the reciprocal of this, I will just negate that. So negative 1 minus 2 to the k minus 1 minus 1. 2 to this times 1 is going to be the reciprocal of the smallest positive normalized value. So let's just distribute that then. I have now 2 to the minus 1 plus, I should point out this is going to be sitting here, plus now 2 to the k, that was in parentheses up there, I failed to have that earlier, 2 to the k minus 1, okay, because this is our bias. All right, that comes to then 2 to the k minus 1, left that off there, sorry, minus 2. And this is all being multiplied by 1. That's the smallest thing we can stick over there. The smallest fractional portion that we can multiply by. Okay, so what's this bring us to? Well, then, This is our exponent, so that's our e. Again, I'm all over the page here. You need to clean this up in your answer. So e is going to equal 2 to the k minus 1 minus 2. What's my m? Okay, well, my m is all of these bits over here plus the implied 1 in front of it. So my m is simply going to be a 1. Okay, because these are the zeros with the 1 implied in front of it. And my f is just going to be a bunch of zeros, so you could just say 0. Okay? What is v going to be? Well, v will end up being then, if you do the math, you'll see that's going to be 2 to the, let me give myself some clean space here. V is going to be 2 to the k minus 1 minus 2. And I'll leave it to you to do the simple math to figure that out. Okay, I'm going to clean this up a little bit here. We need to remember, again, that e is, or the exponent, which we get when we do our reciprocal, is sitting over here. 2 to the k minus 1 minus 2. Okay, so that's the exponent that we want. It's the value of the exponent that we want sitting in our exponent bits. But remember, there's this bias issue that we have to deal with, right? When you look at this, it's by subtracting the bias that you get that 1 sitting right there, okay? So we need to add the bias to make sure that we actually, I need to back up a bit. That was not correct. Please forgive me. Okay. No, what we had was this, okay, is what gave us the 1 sitting there. And this is the reciprocal of that, right? It's the reciprocal of this. So we need to now add the bias to it in order to know what the bits are going to look like that are sitting in the exponents, in the exponent bits in our number. So we will simply then add the bias, which is going to be 2 to the k minus 1 plus 1. Okay, so think about this for a minute. We have 2 to the k minus 1 plus 2 to the k minus 1. Why did I put a plus 1 there? I am having a hard evening. 2 to the k minus 1 minus 1. Okay. So we've got this 2 to the k minus 1 and this 2 to the k minus 1 minus 1. What's that give us? Well, 2 to the k minus 1. Well, if this is the k minus 1th position, let's try that a little differently. I'm going to shrink this down. Let's try again. Okay, so this is the exponent we want. We need to add the bias to it so that we can store that properly, because the bias will ultimately end up being subtracted from it. So we're going to add to that 2 to the k minus 1 minus 1. And we want to talk about what do the bits look like. Well, 2 to the k minus 1, what is that? Well, that's a 1 in the 2 to the k minus 1th position, followed by a bunch of zeros. Okay? What's 2 to the k minus 1 look like? Well, that's going to be a 0 here with a 1, with 1s in all of those positions. Okay, so if I add those two things together, what do I get? Well, I would have an exponent full of 1s. However, I'm having a hard time in my copying. I put a plus 2 there. That should have been a minus 2, as you see right over here. Okay, I am subtracting a 2 from this. So I will have a 1, a 0, a bunch of 1s, all the way to the end. So my exponent will look like that. It'll be all 1s, except there will be a 0 in the second bit from the left. Okay? Wow, that's a fire hose. There's no way that we would have gotten through all those in class. Of course, we wouldn't have done nearly as in-depth of an explanation as well. Obviously, these slides, if you were to just look at this as it is, it would be very confusing. Hopefully, if you're following along, you're able to follow my thinking. My purpose in this was to actually show you the process of dissecting the question, what was being asked, thinking about the representation, so on and so forth. This is probably what my notes page would look like. This is not what I would turn in, and it's not what you should turn in. Okay, this was to walk you through, again, walk you through the thinking, walk you through the decomposition of floating point format and the things that the question was asking for. Okay, so what should you do? Well, you should do what I would do if this was my homework. I would then take the solutions I computed in my notes and put nice, clean, orderly answers in my homework submission, and that's what you'll be expected to do. But this should give you lots of ammunition to be able to do so. The answers are there. All right, I'm going to let you go now and get some dinner. Go get some dinner myself. I'll see you guys in class, and until then.